Hyderabad. Now, Chintan sir has a very vast experience in the field of ASIC design. Now, he has not worked in the ASIC design. He has not only worked in the ASIC design, but has visited foundries in Taiwan and US also. So, I request all the audience to get maximum benefit from him. So, I hand over without wasting much of time, I hand over the stage to Chintan sir. So, Chintan sir, please.
Sure, sure. Thank you, Alisha. Hello all. Good morning. First of all, thank you very much for inviting me to give my nuggets of my experience in the ASIC semiconductor field to audience sitting from Parole University. And I wholeheartedly thanks to Parole University as well for using technology at its best in COVID-19 time and reaching out the students and faculties and industry experts to reach even we are not able to meet the face-to-face. So I think this is the right approach given the situation and whatever infrastructure available. Using technology, we are getting connected to each other. So thank you very much, everyone from Parole University and Yogesh and Haris sir. Just a brief introduction. I'm Chintan Panchal. I'm in my 20th year of learning semiconductor industry. Started my career in 2000, having working with different organizations, different countries, and now in my capacity working in InfoChips and Aero group of company from last 15 years and handling the one of the portion called design for testability. It's called popularly adopters for any ASIC or any chip in the field of the TFT. So I think today I have been asked to give you an introduction about what are the scope of career opportunity in ASIC VLSI and semiconductor. So I aptly created very in-depth presentation and that is having a lot of micro details as well. So unless you guys sitting there ask me right question, the session may not serve the best utmost purpose as well. So I request anyone, if anybody is having any doubt at this moment, ask immediately. Because I strongly believe if you don't ask it out, if you don't ask the question, you will be fooled for time being. If you ask the questions, you will be fooled for the time being. If you don't ask the question, you will be fooled for your life. So I strongly believe in that philosophy. Okay. I believe my screen is visible to you.
Yes, sir.
First screen. Okay. Sure. Let me start. So in my agenda, I'll go through this topic called agenda will be like VLSI path for advanced chip in design. Okay, let me explain you my previous slide. So slide is like career opportunity in ASIC VLSI and semiconductor. So what does it mean like? So I should have to make you aware that what is an ASIC VLSI field, what are advanced technological strengths in VLSI and what are the current challenges as well. So I'll give you insight of each latest trends and everything. So my agenda is like VLSI path for advanced chip design, lower technological node and its issue and power management, and then chip design process in VLSI, how one chip gets manufactured, challenges we are facing real time and few case studies. Out of this agenda, I think my slide is spread across more than 70 or 80 slides. So I don't know if you cover everything, but I'll try to make sure that in next 15 55 minutes, we'll get aware that where you want to make career in VLSI, if you want to make it. Okay. So let's see. I believe being electronics engineer and electronics faculties, he's our father for our careers. Gordon Moore, he's the founder of Intel. What he says that number of transistors and resistors on a chip doubles every 24 years. Are we agree on that? Let me ask that question. Anybody from faculty, students, audience?
Sir, they can only live, but they cannot give the
They cannot
answer.
speak? Oh,
yes.
Okay.
And sir, please speak loudly. Speak loudly.
Oh, really? Okay.
Yes.
Is it? Does it mean that my audio is not full?
Yes.
Better now?
Yes, better.
Okay. Let me go to full screen again on my. Okay, Gordon Murray is our father. He's the founder of an Intel. Uh, in 70s, early 70s, he predicted the future of ASIC semiconductor. First chip when he manufactured, he gave this prophecy that, according to him, transistors numbers will be doubled every 24 months. So, what does it mean? So, let's say today, if I have 100 transistor in a chip, manufacturing chip, maybe next 2 years, the transistor numbers will be increased from 100 to 200, 200 to 400, 400 to 800, 800 to 1600, 16 to 32. That way, every 24 months, size number of transistors will be keep on increasing. And believe me, even after 2022 decades, this prophecy is still true. I'll tell you the example as well. So he's the driving force for ASIC VLSI. So anybody is having doubt, bring this statement into your mind and put it in read-only memory. Intel is the biggest company in the world for semiconductor, will never let his father's statement die. I can guarantee that. Here's the trend. Here's the data point. Evidence. I'm not flying the kites in front of you, but you see, in 1970s, 1980s, 90s, 2010, 2020s, the how Moore's law keeps alive. Like in first chip which manufactured in 72, 73 was having 4,000 transistor. After a couple of years, the transistor size in one chip in processor called 8008 particular processor, the series of 8080 and then 8086 to 86, the transistor size keeps on increasing from 10 raised to 3 to 10 raised to 4, 5, 6, and 10 raised to 9. So coming down to these are the 8, 17, 16, 17, 18 data, the i7 and then Ivy Bridge, they are having billions of transistor in a single chip. So this is the evidence of transistor in a single chip. Single chip, when I say that single chip, one chip which you open it, it contains this many number of transistor, irrespective of technological node. It can be 32, it can be 28, it can be 16 nanometer. So let's say, I'll skip my company's introduction. We may get a chance to present in campus mostly, but let me skip it. Okay. I'll give you this. This is very insightful slide. How a semiconductor industry is spread across in an ecosystem, how it makes an ecosystem. So, uh, anything comes with some design concept. So, the lower oval is an info chips design services company. The center oval is an ESLA. On its system level companies like Apple, Cisco, Intel, ASUS, Motorola, Samsung. These are the companies are actually manufacturing some application-based chip that is called an ASIC. Now, what are the inputs for them? The inputs for them are some IPs. IPs come from IP vendors. So let's say one SoC is having memories, some USB controller, some UART controller, some processor. So those comes from the IP vendors. So ARM is a company providing processor. Memory vendors like Micron, Samsung, other companies are making memories. They provide the memories to assemble those components in one chip by ESL companies. So IP vendors are essentially vendor. They develop their IPs and sell it to the ESL companies. Now, how come those IPs gets developed? So then comes that left top area are research institutes, academias like MITs, then IITs, NITs, and several universities where research are happening. So they do some research, IEEE research, come up with the protocols and something, and based on those protocol, the IP vendors develop their own IPs. So I can give you an example. Let's say PCI, peripheral component interconnect bus. So PCI 1, PCI 2, PCI X, PCI Express. These are the protocol developed by Research Institute. Wi-Fi, let's say Ethernet protocol, 802.11, ANG, and different standards. So those protocols has been developed by Research Institute. Those protocol has been understood by IP vendor and developed an IP using Verilog, the hardware descriptive language, and then those IPs gets verified, simulations correct, and then layout has been done successfully, those IPs goes to ESL companies. Now HDLs, when I talk HDL called Verilog VHDL hardware descriptive language, it required some tool to process the code which you have written. So that requires EDA. The left side, my middle segment is an EDA company, electronic development test automation. So companies like Cadence, Synopsys, Mentor, uh, IXIA, Wind River, these are the companies which generally develops the EDA tools that we have to essentially use to process our code IP for semiconductor development. Then on right side, if you go, that is called an ODM, original development manufacturer. So like different companies like Quanta, Gemtech, Flactronics, they develop original. Let's say if I want to make one, let's say what I would say, processor. So processor have DMAs. So DMA and those sort of GPS or Bluetooth. So those IPs, not IPs, I would say, but system. This ODM manufacturer keeps on developing and providing the ESL companies. And then what you will do with these all components when ESL companies receive those components based on their architecture, they assembled it, put it, and then the companies like Infochips, which provide their expertise in design services, given it RTL design, given it verification, given it physical design, given it TFT, we do our services work with those companies, and when we do tape out, the tape out netlist will go to the foundries, the right middle circle. The foundries like TSMC, UMC, Global Foundries, Semiconductor Complex India, Chandigarh, which is little old now. So these are the foundries actually making one chip. So that is also a big setup. So to give you an idea, the ecosystem of semiconductor, these are the horizons, or I would say that horizontal buckets where any electronics engineer can find their job, given it ASIC service company, Infochips kind of companies, the EDA companies like Cadence, Synopsys, Mentor, and some more, IP vendors, ARM, then different IP vendors, many IP vendors, memories company, Microns, and everything. Then ODM companies, and then foundries. These are the different horizontal buckets, the group of companies or group of career builders where any engineer can find the job, their careers in this ecosystem. So I hope I'm clear what I'm trying to say. Harish, sir, if somebody can acknowledge, if you guys can understand. I know everybody is not able to understand, but at least few guys can understand this thing what we are talking. Okay, going to my next slide. So here, so this is like the stack, the product development stack, electronic product development stack, I would say. So how it gets developed? Let's start with the bottom layer. So bottom layer are actually the like some particular protocol, some technology, let's say wireless technologies, GPS, satellite technology, Bluetooth, microwave, Ethernet, optical network, wired network. So based on these different protocols, we required some hardware. So what does it mean? Hardware means some PCBs, but not only PCB. PCB required some chips as well. So we need to develop ASICs or FPGA that has to be verified, that has to be like physically designed as well, and then post silicon bring up activity and validation process to be done. So this is second, the cursor which I'm moving, actually the ASIC development cycle where all the hardware gets developed. So any engineer, any interested person is getting excited by these different protocols, technologies, and inspired to work in the field. They can choose to be in hardware field of semiconductor. Once you have hardware, let's say, you have hardware processor ready. Now, how that processor should work? So it has to be on motherboard. The motherboard has to be interacted with different peripherals and everything. So what does it require? It requires some firmware. So the firmware, like I have my chip, which is like working on some specific language, maybe processor, let's say ARM processor, it required C language or assembly language. So, and then assembly language, not all the user understand. So then it requires uh, uh, somebody has written an operating system. That operating system is a piece of purely a software, but then C language operating system cannot be understood by my hardware, the processor. It works on assembly language. So the firmware area which bridges the gap between software and hardware. What does it mean? That the firmware development verticals are developing a system such a way that it can interact with the operating system of the software with the hardware. So there is a vertical called firmware development, where any enthusiast with the software coding style and then have some knowledge or interest in hardware interaction, they can choose to build their career in firmware as well. Then third stack on top of firmware is a software. Any engineer which is having sound fundamentals of software development, having good logical reasoning and everything, they can go and make an application software or embedded software. Once hardware, firmware, software combines, it becomes one end product. So that is like product engineering. So these is like ecosystem for any electronic product design. You beat any company anywhere, it has to follow largely this development stack ecosystem: hardware development, firmware development, software development, and product engineering. So I think this has to be understood very clearly. If anybody wants to make a career in semiconductor, they have to find their skill mapping as well. Not blindly go into hardware, do not go blindly into software development. Based on your own skill set, your own interest, you have to carefully choose it. Otherwise, you may not able to do justice to your career development or an organization which you choose as well. So make a chart out your skill and map out in which area your skills are having strong weightage. Going to the next slide. This is what latest technology we are working on. It's an example like automotive industry, how semiconductor in proving their value. The car, it required some silicon, let's say. So all the car, not I would say car, but the automobile vehicle are nowadays an electronics. So any electronics, it requires an listed hardware. Hardware, that means a chip, ASIC, it can be controller, it can be processor, it can be full SOCs, anything. Once that silicon has been developed, it has to go into some platform, so motherboard, and then the PCBs design, and then firmware development, and then software. Software will go into some system, and then system will put inside your vehicle. And based on certain analysis, human decisions, or GPS tracking and everything, you can control your vehicle. So this is an example where silicon industry is making an impact. This is just an example of automotive industry. Be it anywhere in your day-to-day life, electronics engineering is an essential part. And when I say electronics, that means a semiconductor, ASIC industry. I'm making pause here. Maybe somebody who can raise the question, wants to raise a question. So this is what we called an ADAS system, Advanced Driver Assisted Car. So that's where we are like, ASIC industry, semiconductor industry are making more and more impact. Worldwide, the usage of automobile is keep on increasing. Everybody wants high-end and full-featured vehicles. Given it's two-wheeler or four-wheeler, mostly four-wheelers, it has to have a very advanced technology to reduce the risk of human life. We are using the technology. So these are the ADAS system. Multiple features are there. Advanced driver assisted system. Okay, so here is the block diagram of any broader level block diagram for any chip development. What are the components lying on hardware architecture? So any chip, which we call as an hardware, the architecture components are basically having 4 to 5 categories, which has given in this different rectangles. So let me start. So any ASIC or SoC or a processor, it essentially will have some storage element that's we call the memory. So memory can be SRAM, DRAM, maybe NAND, solid state drive, serial flash, MMC, EMC. So these are the different component of the memories. And then based on this memory, we can put it, just hold on. Based on this component, we put it on our chip designing architecture. So let's say if you need some specific memory, so use this SRAM only. Some architecture required only serial flash. Use the serial flash. Some memory required NAND solid state drive. So use the solid state drive. So those are the one of the component called memory. So now if I move to another components in building block, maybe connectivity, communication protocol. So the left bottom are the component called GPS or Bluetooth or control area network. These kind of communication protocol are essentially built inside your chip to communicate with the different systems. So every protocol, GPS, Bluetooth, control area network, FlexRay, OBD, these are the protocols defined by research academia, and we do develop the IP, and IP essentially go into ASIC development. And another components could be like, let's say, like how do we connect? Like it has to be connected through slow interfaces. How do interface to the real system? It can be SPI, it can be I2C slave. So these are the UART, USB, anything. So these are the interface protocol are essentially a building blocks for any SoC. And then let's say your graphical presentation called cameras and sensors and everything. So MIPIs and lower, my cursor is moving lower bottom, like MIPIs, CCD, CMOS. These are the sensors which are essentially used for your uh, the system development. Yeah, let's say your mobile is having camera. So how do we integrate camera, which are the analog, like connect the you click the picture, which is maybe video, live, audio. These are the analog in behavior. It has to be processed and stored into digital format. So these are the protocols as required to develop these IPs and become a building block for any SoC. Now go on middle top. Those are the displays: HDMI, LCD, LED, touch controller, display. These are the different building blocks for display related units. So as these again, in terms of IPs or in terms of logical core, sitting inside an ASIC. Then there are some sensors as well. Now you must be remember that 4 to 5 years back, we have this 6-axis gyroscope came into the picture. You know that your phone, you can change the orientation, horizontal, vertical, or you may, you see that there are few games where based on level, you move, racing games or flight simulator or something. Based on position of your phone, you can drive the game controls and everything. So this is possible because of the sensors and MEMS. What is MEMS? MEMS is like micro electromechanical system. So that means there is a mechanical part connected with the electronic system in a single chip. So that is again a very cutting edge technology, I would say. These sensors are essential and analog part. Those are interfacing with the real world, and provided that input has to be converted in digital so that my digital system can understand. So the MEMS and sensors are essentially a very promising field for ASIC VLSI as well. Then on right bottom, the power management stuff. But nowadays, the chip which I'm working are having more than 500 billion transistors. So Using 500 billion transistor is a huge number. Assuming, let's say, you must have experienced your phone sometimes when you seeing the video while some background applications are running, let's say GPS are running, Bluetooth is on, your phone getting heated a lot. So that's the reason, like a lot of IPs, lot of logics are getting toggled, getting power. So that power consumption keeps on increasing, and it is gulping your battery power. How to reduce that? So it requires a lot of logic, a lot of different controllers like low power ESD protections and power protections, low noise and analog circuits and power circuits. So these are again right top, right bottom components are different logics or areas where any ASIC engineers can make their career. So this is very nice architecture slide I have put, very general, where any enthusiast electronics engineers having interest in hardware development can make their bright career. Going to my next slide. The embedded software, I'll not speak too much, but yeah, as I said, all the hardware, the ASIC has to be work with their operating system. That's called the software. So it requires the embedded software, not necessarily my operating system, Windows or Linux or Symbian or iOS or Android can directly work with any hardware. It requires their own specific software development. So different devices require different type of drivers. So this is what I'm talking right now. So any ASIC industry, any engineer, electronics engineers having bright future again in embedded software development as well, VLSI software development. Avionics is again an industry where there is a huge need of electronics engineers. So if you remember, there was a flight MH370 disappeared a few years back. We don't know how the world is still searching out where the whole plane more than 200 passengers vanished. Okay. Even though it was having highest safety standards and properly implemented, nobody knows. That means still there is a huge scope of development and research scope available in avionics industry as well, where the safety is the highest critical requirement. UAV like UAV unarmed vehicles, and then the drones and everything are required ASIC industries to develop different hardware to support their advanced features and everything. It requires some different standards as well, DO standards. The future car, this is what the one project one company we are developing the system where, like, if you are driving car and there are back-to-back cars, the sensor installed on, focus on this picture, the sensor installed on the road side, it detects the driver position and it detects the previous car and distance, and send an alarming signals if you are too near to a car in front of you or near to car in front of you. So that way it increase the safety and everything. So like these are the future cars. Maybe people might have aware that Uber has started driverless car as well. So this is one of the application where ASIC semiconductor industry has started their application level a few years back. Smart city. Okay. IoT is a buzzword these days. You know that Internet of the Things. A lot of gadgets, a lot of systems are interconnected now. This belongs to ASIC hardware development as well. So now, based on several studies, what could be the market for IoTs by next 2-3 years? So in 14, 15, 17 onwards, you see numbers are keeps on increasing. Not, I would not say linearly, but somewhere non-linearly as well. So by this year, it would cross 491 billion. Next year, 675 billion, and even by 2022, it could cross 880 billion as well. So it's a huge amount. I'm talking 880 billion US dollar. So that's a market potential. And this 880 billion comprises semiconductor portion as well. The pie of out of full 880 billion, there is a small pie goes into ASIC industry as well. So this is a very promising. We have a lot of scope for ASIC industry, semiconductor, where IoT, the new technology, will boost up the semiconductor field as well. Okay. So 50%. You see bottom color coding. If you go see that hardware development is and platform development, the lower two bottom. So out of 100%, 15% will be the market for ASICs, purely an ASIC semiconductor, and then hardware and hardware and firmware development, platform development is 29%. So 29 and 15. So almost 45% market is available out of 880 billion into ASIC semiconductor for IoT applications only. So that's a huge market. So lot of scope is available. And the most importantly, service industry. Service industries like Infochips, Wipro, these are the companies are sharing 34% of the market. I will not speak too much. This is too technology and commercial slide, but then let's keep it for time being. How IoT system works. In 2018, when I returned from US, I was not sure whether I'm going to stay in India, but certain reasons I stayed in India. But for a few months when I was in India, I was able to control my home sitting in India in US. My house is in San Jose, and I carry my phone where the application installed, and my home was having my broadband connectivity, GPS system on, AT&T card, and then I used to pay my bills. I used to control the humidity, air condition, electricity usage, and everything sitting in India. So that's an application of IoT. So this is what I'm talking about: the iPhone app, and then connectivity through Wi-Fi or GSM, and then energy consumptions and the security alarms and video analytics. Who comes to give something, some parcel comes, some post come for me or something. That everything you can look at and control from anywhere in the world. So that is one of the application, and we are assuming that at this moment, one like some of the customer which we are working is having 1 million connected homes. So that's a huge potential. 1 million homes are connected. A huge potential. Again, this is too technical, the case study. This is okay. Before going into that, let me show you one video. How one semiconductor uh, chip gets manufactured. So I don't know how I keep my video there. Yes, video, you guys are videos, audio is coming. I'm playing video, but it is having some audio. Is anybody hear audio there?
No, audio is not coming.
Okay, I don't know. This is my VLC player and my local video. How do I provide that audio to you? I don't know. But anyway,
No problem.
this is like one chip, which is Intel in 2017-18. They made 22 nanometer. So just enjoy how one simple component called sand. Everybody must have seen the sand. In the sand, the bright small particle, crystal sort of particle you must have observed when you see some river sand or something. That's called a silica. So using that silica, how one manufacture wafer ingot gets manufactured, and then wafers, and then single transistor gets manufactured. This is the video, 2 minutes video. I'll go with the pause as well. Please enjoy. Very informative and very nice video. This is very exciting. These are the sand particles. They collected the silica out of sand. They burn it, and then pure silicon ingot created. silicon ingot has been cut in the wafers, a 9-inch or 7-inch or 12-inch wafers, the single wafer. The cleaning of the wafer is happening. Then photosynthesis. These are the process actually happening in manufacturing wafers. Impurities, semiconductor creation. Now, how this one single 3D transistor gets manufactured? Substrate and then N-well, B-well. Channel creation. This is again a single transistor. Voltage domain creation. Etching process. Polishing. Millions of transistors and then wire connectivity. 1 layer, 2 layer, 3 layer. The one ASIC, single ASIC. This is one single ASIC connection in chip. The multiple ASICs in a wafer. This is one processor. It has been cut in single pieces. Yogesh sir was calling. Just let me take. મારે કનેક્શન ચાલુ છે. અચ્છા ના મારે કનેક્શન ચાલુ છે. તમારે એટલે મારો સ્ક્રીન નથી દેખાતું એવું છે. ઓકે ઓકે. Okay, so that is the video of one chip, one processor creation by Intel. So let me just go back again and stop some. Here I would pause. So you see base layer, the bottom layer is actually the transistor, maybe 100, 200 million, 5 million, 50 million transistor on the base layer. And each transistor has to be connected, gate, source, and drain. Okay. These connections are basically, these rectangles are wire. Those are connected by multi-layers. Like multi-layers, you assume that there is a 10-story building, 5-story building. So each wire goes, let's say, first layer, all the wiring. Now I have wiring, some wiring has been done. Still there is a pending wiring. So now, but there is a congestion on first floor. So wire has to be go and stretch to second floor and then do other wiring. Still there is wiring pending, but there is a congestion now on second floor as well. So you go to second layer. So this way, like currently we are working more than 11 layers, 10 layers, 11 layers of physical design of chip manufacturing. So that means up to 10 layers we are going to do wiring to connect this all 500, 600 millions of transistors. So this is what I'm talking. So if I know a little bit. So these wirings are 1 layer, 2 layer, 3 layer. You see, these are the layers. And one single chip might be having long wiring. I have my very favorite example of Apple Bionic processor 11812. So it's a 10, I would say that 100 mm square chip, 95 to 100 mm square chip, it's 10 mm cross 10 mm. So very small button size. You see your button is having 7 or 8 mm diameter. So button size of processor having 200, 400 billions of transistor, the wiring length to connect those 400 billion plus transistor is somewhere more than 4 to 5 kilometers. single chip, single processor, button size, connecting all 400 billion of transistors, it requires at least 4 to 5 kilometer long wiring. So this is evident from this video. See how long wirings are there. Complex. Very complex. So I would say that this is what I'm talking about on ASIC field, ASIC development. So coming back to my slide now, let me go into the slide I was talking on the MEMS ASICs, where we worked with InvenSense in 2016-17, where the Apple comes with the gyroscope applications, the motion detected chip where play the game. Your phone can be a gaming zone itself. So, micro electronic mechanical system. So, you see the six-axis mechanical part. It's called the gimbal. The rotor part and axis, pin axis. This is actually a mechanical part, and that mechanical part is assembled inside one electronic chip. So it's not my any transistor detect your motions. Any motion detection has to be is an analog in behavior. That analog behavior has to be detected by some sensor. So this gimbal acts as a sensor, converts that analog signal into digital, and then based on digital input, my chip gets working and do the rest of the processing very fast. So this is called a MEMS. So very bright future again for any ASIC development. So what is an application area? So these are the application area, the sports wearable, IoT systems, and then your embedded device, your iPhone, iWatch, or any watch, the speed controlling, automobile industry speed control, motion control, and everything. This is based, the main function, the main hardware which enables these functions, safety functions or applications is this MEMS ASIC. So the different scope of work where we work as an info chips, like RTL design and FPG prototyping and verification and physical design and creative services and then validation part on FPGA. Okay, the 3D axis structure. This is something very interesting to understand, like how Moore's law is alive. Instead of understanding 3D, let me give you a very generic statement. Everybody is aware that core 2, dual core, that I3, I4, I5, I6. So I7. So what are those? I3 is like third, 3 core, I5, 5 cores. So what is the core with? So when that core duo starts and core to dual core, the dual core means the single processor having two cores. Now, the two cores was doing some functions perfectly fine, but then application required some more processing power. So what Intel comes with the solution? Increase one more core in a single chip. So instead of two core, make it four core, six core. That way they increase the core processing power, but the processor is one single chip only. Inside that one single chip, multiple cores they have introduced. So the cores are basically how they work together is like in this slide you see die 1. So consider die 1 as a one core. Similarly, there is a die 2, die 3, die 4, die 5 are different cores sitting together on in a stack on a single chip. So this is the fundamental architecture of 3D structure. So again, this is very bright future. The 3D ICs where you can reduce the number of transistors, you can reduce number of areas, at the same time you can satisfy the Moore's prophecy by doubling the transistor every 24. So this is the real example right now. Like you can keep on increasing die stacks, one stack, two stacks, three stacks, something like that. Very interesting. Currently, EDA tools are also working to make their tools mature to support this technology. So very heavy future is residing there. For 2.3D IC, we actually work on a project with Intel on 2.5D IC. wherein we involved our team to manufacture this chip on one core and then a few memories on different technology. When I say technology, means digital logic core is like 16 nanometer and memory is on 32 nanometer. That is a 2.5D IC. And gaming, this is Toshiba project I'm talking about. We how much time here? BFT wireless. This BFT is a business unit where I represent. We call as doctors for MG. So go there as well. This is radiation tolerant FPGA development for microscopy. There are few FPGAs like nobody can tinker. These are the space applications by some government like NASA's and ISRO's and some military very secure product wherein nobody can interface that requires radiation tolerant as well. So these are very security security tight product wherein uh, like snooping of the data is not allowed. So very strict protocol we have to follow. So that's where like scope like the satellites. You know that why how come satellites which are in space are not getting hacked as well. So based on such kind of hardware, China's satellite can provide data to China only, but then no very thin possibility. I can't say that because I don't have data, but then very thin possibility that we can get data from China without their permission as well, or vice versa is true as well. So it is because of this type of hardware ASIC development. Nanometer program. These are basically case studies what we are working on. But I want to more basic information. Okay, again Moore's law came. So let me explain. This is my very popular example. Like you see, Apple A13 Bionic processor, which consists 8.5 billions of transistor. It's a 7 nanometer chip, 7 nanometer technology. That means the gate channel width is a 7 nanometer, manufactured by TSMC, Taiwan Semiconductor Manufacturing Company. The die size, you see, area is 9800 mm, the 100 mm square. So that means 10 cross 10. So 10 cross 10 mm size of processor consists 8.5 billions of transistors. Immense, very immense. This is one processor, but there are networking chips as well where we are working having more transistor. The one chip which we are working on having 400 million plus flip-flop on it. The one flip-flop based on technology can be made using 6 to 8 transistors. These are the slide I'm browsing through quickly, just justifying that Moore's law is not going down at all. It will be still surviving next decade, I would say. So how it is still alive? This is some interesting example. How the chip, the size of the chip is not getting increased, but the number of transistors are getting assembled in the similar size. So this is the slide I want you to understand. So let's say uh, uh, the question is that the human hair, the diameter of human hair is somewhere like 200 to 600 micron, 10 raised to minus 6 meter, 10 raised to minus 6 micron. What we are talking today, the technology at 7 nanometer, the chip which we are working are 7 nanometer and 5 nanometer. So this is how like the same area of chip, the die size has been reduced because we are able to reduce the channel width. So earlier we started with chip in, if I remember, with Semiconductor. I was working on capacitor and reverse oscillator, which are on 118 micron, 118 micron. So like it comes around somewhere here, like 2 micron to 3 micron. Then it keeps on reducing this area. So when you reduce, when you go the geometry reduced from 3 micron to 2 micron, the area reduction is 0.5x. Similarly, if you keep on reducing the area from 3 to 1.51 and then 700 nanometer, 400, 130 nanometer, 90 nanometer, and up to let's say 7 nanometer. So at every stage, your area gets reduced, and then your area gets reduced. That means you can accumulate more transistors. So 0.5, half of area reduced. So that means you can double the size of, double the number of transistors. Half of the area, if half of area one, initially if I have 100 transistor, if I reduce the technology from let's say 90 to 65 or 130 to let's say 90. So if I have 10 mm square area occupied, if I reduce 130 to 90 nanometer, my area reduced to 5 mm square. So remaining 5 mm square, I can accommodate almost that size, that number of transistors. That means I'm every time when I reduce the technological load, I'm able to comprise double of the transistors. So you see, every couple of years, the new technological load keeps on introducing. To last year, 2018-19, we were working on 7 nanometer. Now, after 7 nanometer, Intel has started the prototyping in 2020 on 5 nanometer. So that means 17-18 and 2 years, 5 nanometer. I'm not sure. I'm very hopeful that after a couple of years, it can be 35 angstrom, 10 to minus 10 as well. Carbon nanotube is in the latest example. Everything is transistor size keep on reducing. The area keeps on remaining same, so you can keep on accommodating more and more transistor. And then this is the data where this data has been practically generated by certain engineers, electronics engineers only. So that means all the slides which I have shown you is not theoretical book slide. These are all real life practical data collected from several projects, several companies. So that means some electronics semiconductor company has produced those data and I have collected it. So my point is, every stage you can find your job, every stage you can find your career. So this is the future for any electronics engineer, very bright future, I would say, if only if you have enthusiasm and craving to do electronics engineering job. This is something more detailed explanation, the teaching and everything. I'll not go into too much detail. Same thing which I spoke, this is explained in visual slides. Okay, so technological trend. So here technology evolves, like if you see, we started the transistor radios. So old days there was a radio, the huge diodes and everything. So focus on that diode transistor involved. Okay. Then 58, the small ICs. A small IC was manufactured by Intel, huge transistors and everything. The 4004, the interface IC 71 by Intel, then mobile phone in 73. So if you see the technological trend, every 5-10 years, there is new technology keeps on evolving. 2009, 4G, now 2018, I talked on FinFET transistor, 2007 nanometer, maybe 2020. I'm already working on Intel, working on 5 nanometer, and we are involved as well, the prototyping. So this is what we are talking, 2020, 5 nanometer. And then there is an IoT based application like artificial intelligence, 5G, 6G, 7G. So this graph, if I connect this all the dots, is always going on progressing. It's not sinking anywhere. It is not going down anywhere. You see. So this is the scope of semiconductor industry. Again, I'm justifying why Moore's law will be alive. Different technical data I have compared. The point I'm trying to make is that the new technology which which is carbon nanotube, single atom transistors. These are the driving force of upcoming technologies. Believe me, there will be a huge change. Currently, the IoTs and 3D printers, and these are the applications. But now Moore's law has to be alive, so that requires next to FinFET. That's a CNT, possibly a future. Then single atom transistor can be a future as well, or Heisenberg uncertainty as well. So these are the driving force for next decade, 20 onwards, 2020 onwards. The detailed slide again for each transistor fabrication process and everything. And it's very high level of technological data. I don't want you to bomb up getting your mind to be full with more complex technology. But my point I'm trying to say that these are the driving force for next decade for ASIC semiconductor. The comparison between FinFET and CMOS, you go into your theoretical lectures as well. The FinFET, what we can do, tunnel FinFET, tunnel FET transistors. Tunnel FET, there might be a possibility. Tunnel FET, these are the slides I wanted to see. And BEF wire, and BC FET. Next generation lithography is again transistor level, not much we can do, then the lithography process has to be improved as well. So these are the reasons why lithography process can be improved as well. So conventional lithography, number of wires getting short while doing this manufacturing of the chip, like double patterning can be used and different technologies can be used. And these are the new technologies are in concept. That means the concept has to be go into actual implementation and real application. So quickly going to, because very technical stuff is there. I'm always open for another technical sessions as well with you guys. But this agenda, I hope that it's satisfied to make you clear that there is a huge scope for career development in ASIC VLSI. There is no way, otherwise I would not be doing this presentation. I have still my few years to go in ASIC VLSI. Yes, Yogesh sir. Any Harish sir, some
Yes,
question?
sir.
If I can pick up.
From the participants, one question from the participants, that
Sure.
anyone want to start the career
Mhm.
in VLSI,
Sure.
then what is the right way to start a career?
I would say right means that the spec which I shared with you, like any engineer has to find out that area of interest and competency skills. Like if I'm very good in understanding logical design, yes, then I can go for semiconductor. Now let's see, if I go to semiconductor, where should I go? So there are total 4 verticals. Let me see if I can give you that somewhere. We have these 4 basic verticals, like design, RTL design, then verification, and then physical design and DFT domain. So person can choose out of these 4 any business unit or any verticals. Let's say I'm good in coding, or I'm good in logical design and verification, I can choose verification. I want to do physical design, actual wiring and actual the placement of the component and everything, I can choose to be in physical design. And that a chip doesn't work and I want to do diagnosis, doctor's job, they can do the DFT as well. Of course, at your stage, at an engineering 6, 7, 8 semester at campus, you might not be aware about this thing, how it is happening. That is our job to get you trained inside these all 4 verticals. But your start point should be your area of interest. Okay, I'm good in doing this. First of all, you have to have that internal judgmental skill that, oh, I'm good in this, so I'm good, I can make a career out of this. Then rest of the things, the company who choose you, will be in their hand. There are hands-on training programs by a separate company. At least in my company, I am owning the training programs for physical design, DFT verification, where in 6 months after you got selected in campus, we have 6 month training program where we will teach you each and every aspects of VLSI technologies, and then we will put you on certain projects.
Okay, thank you, sir. Thank you, sir.
Sure.
Are sir?
Okay. Okay. So,
Are sir?
is it audible?
Yeah, you are
Yes.
audible.
Sure, sure. So, shall we conclude here?
I
Yes,
think so.
sir.
I have hard stop at 12. I have another meeting.
Yeah, yeah, yeah.
My HR head is waiting.
Yeah,
So,
yeah. So,
but yeah, I can take up one
very,
more. Sure.
yeah. So, thank you, sir, Chintan sir, for sparing your valuable time with us. I would just like to conclude with what you have done. You have started with the Moore's law,
Mm-hmm.
then semiconductor ecosystems, electronic
Uh-huh.
product ecosystem, example of automotive industry,
Yes.
example of avionic industry, IoT future technology. Then
Yes.
you have shown the nice video of semiconductor chips and very
That's right.
architecture, and you have discussed very nicely the end of the Moore's law, whether it is going to be end or not. So you
Sure.
have nicely explained what you wanted to say, right? So I hope that all the audience might have got the inputs, valuable inputs from you. Thank you, sir. Thank you very much.
True. True. Feel free to drop me an email question in an email as well. I will try my best to answer those questions as well. I have
Okay.
seen 190 slides, so we all only go up to 60 only. But yeah, I hope but that we justify the purpose of this meeting at least.
Okay, sir. Thank you, sir. Thank
Sure.
you, sir.
Thank you very much.
Okay.
Have a good
Okay.
day. Yeah. Take care. Yeah.
Okay.
Thank you. Bye
Okay.
bye.